In this video, we will look at amplitude modulation, AM for short, a technique that was widely used in the early days of radio broadcasting. Have you not come across it before? Well, ChatGPT comes to the rescue. In short, we employ a carrier signal which has a high enough frequency to make the size of the antennas relatively small, and we encode the information that we want to transmit in its amplitude. At the receiver end, we recover the envelope of the signal, i.e. the changes in the carrier's amplitude over time, and this gives us the information that was originally transmitted. For example, if I wanted to transmit a 1 kHz warning tone, I could simply make the amplitude of the carrier signal vary at the same rate as a 1 kHz sine wave. At the receiver end, I just recover the envelope of my carrier signal and reproduce the 1 kHz tone. Let's go to the lab and make it happen in real life. Most function generators offer modulation options. Here I have set the carrier frequency to 10 MHz, which is still a bit low, but will make your antenna 10,000 times smaller than it would need to be for a 1 kHz signal. And I've set the amplitude to 2 volts peak to peak. Now I can turn on the modulation, set it to AM, and set the modulation frequency to 1 kHz. This generator even gives me a pretty accurate sketch of what my waveform will look like. Now let's use an oscilloscope to visualize the signal in the time domain. Things look a little messy here, and that is because the time base is set for the 10 MHz carrier signal and its amplitude is heavily modulated. To see a waveform that enables us to identify the envelope of the signal, we need to increase the seconds per division based on the period of the modulating wave, which is 1 millisecond. So, if we choose 200 microseconds per division, we should be able to have a better view of the modulated signal. And indeed, here it is. It's moving all over the place at the moment, because the scope's trigger is struggling to keep up with all the amplitude variations. Ideally, you should use the signal's envelope for your trigger, but my trick is to push the trigger level as high as possible. This way, there will be much less amplitude variation above the trigger threshold, which stabilizes the waveform. It's a quick and dirty trick. The rate at which the amplitude of the carrier varies is very clear, and it is indeed 1 kHz. If you want to see the carrier itself, just decrease the seconds per division, and this enables us to zoom in to the carrier's amplitude changes. Let's now see the frequency content of the signal by means of a spectrum analyzer. We have 20 of these instruments coming to our labs, and they are super useful. Firstly, I need to set the center frequency to that of the carrier, 10 MHz, and change the amplitude reference level so we don't crop our spectral components. At the moment, we can observe significant changes in the spectrum of the signal, and that's not right. It is all to do with the resolution bandwidth of the analyzer, which needs to be set correctly to display the right frequency content of a signal. Firstly, let's reduce the span, which is the frequency range around the carrier that we want to display. Here I've chosen a span of 10 kHz. This makes things better already, but in order to see two neighboring spectral components as distinct, we need to decrease the resolution bandwidth, i.e. measure the power over smaller frequency segments. This increases the number of measurements that we make over our frequency span and gives us greater accuracy and granularity. The only downside is that it takes longer for the instrument to sweep across our frequency range. Now, if we reduce our resolution bandwidth down to 100 Hz, we can see the right spectral profile for our AM signal, which has 3 main peaks. Let's put some markers on those with the super useful all markers to peak function. The central component, which has the highest power, is associated with the carrier signal. The two components either side of it are called sidebands and are separated from the carrier by the modulation frequency, in this case 1 kHz. Now, if I increase my modulation frequency, I should see those sidebands move away from the carrier, and indeed this is what we observe as we change our modulation frequency to 2 kHz, 3 kHz, and 4 kHz. Let's move our modulation frequency back to the original 1 kHz, and let's look at another interesting feature of this instrument. I can select marker demodulation, and then AM, and the instrument will not only recover the envelope, but also reproduce it as audio, as you can hear. Let's change the time to 10 seconds, so that we have fewer interruptions in the sound, and then as we change the modulation frequency, we can clearly hear the changes in the reproduced demodulated signal. So, if we can send a single tone through our AM communication system, could we modulate the carrier wave using an actual song, which is just a combination of many tones? Well, let's give it a go. I've connected my phone to this Bluetooth receiver, which takes the audio from my phone and produces an audio signal at its output ports. These would normally be connected to a speaker through an audio cable. Instead, I am using a jack to B and C cable to connect the audio signal to the external modulation port of the signal generator, so I can use it to modulate our carrier. But before I do so, let's take a look at what the audio looks like on the scope screen. You can see plenty of amplitude variations here. These are due to the fact that the song comprises many frequency components, each with different amplitudes and phases, and they combine together to give us a time domain waveform of this kind. Will a signal of this kind give us more amplitude modulation than we can handle? Well, let's try. Let's connect the audio signal from the Bluetooth device to the aux port of the signal generator, and let's change the modulation source to be external. Now let's play a song and let's look at the spectrum of the AM signal modulated by that very same song. You can see that you don't just get a couple of clear sidebands. The frequency content around the carrier is much denser and changes all the time, as is to be expected. Now let's turn on the marker demodulation function of the analyzer again and see what happens. Well, looks like we made it, but most of our signals are traveling through wires, which enables us to have a pretty good signal-to-noise ratio. But could we carry out this transmission wirelessly? That's a question that will be answered in the next video.